Okay, today we will be starting our unit number 3. So this unit number 3 is quite related to your power system stability. Power system stability. Stability. Okay. So now here you have learnt about in on a single machine system, right? You have done the numerical and swing equation on a single machine system, but we will be doing the same thing for a multi-machine system. Okay, so for a multi-machine system we will be checking the stability, and if there is a fault comes in picture. So basically if we are dealing with a multi-machine system, therefore we are going to use matrices. Okay, matrix, and that matrix will be most will be used for y matrix. Okay, y matrix, as you know, this is a sparse matrix, so it is helpful in calculation. So here we'll be doing we'll concentrating. So basically it's a combination of your power system stability and your load flow analysis. In the load flow analysis you might have built about Z matrix, Y matrix. So it's a combination. Okay, so we'll be taking mathematical analysis of Y matrix and your multi-machine system or swing equation. So first we have to revise what is swing equation and how did it come. So today we'll be just revising on the swing equation. So this is our single machine system, and PS is our mechanical input power. Mechanical input power. Okay, and PE is our respective electrical input power. Okay, electrical input output power. So this if I'm telling this is our mechanical input and mechanical output, that means it's a generator. Electrical output, then it's a generator, right? Mechanical input and output is electrical, so it's a generator. Now this mechanical input develops a torque TS. Okay, so as it is a generator, the omega s, or the speed of the rotor, will be in the same direction of the mechanical direction, right? So these two are in the same direction. Similarly, the electrical power will oppose the mechanical power. Then only every action has equal and opposite reaction. Then only the balancing part will come. So some opposing action will be there, and that is our electrical, and that develops the electrical torque. Okay, so basically, if I tell you there is a relation, this machine has a mechanical and electrical relation, right? So swing equation is basically a relation between relation between mechanical and electrical power. Okay, now as here mechanical side generates mechanical sides has power, also electrical sides has also power, but the parameters that mechanical sides have to define a power is a different for electrical power. Just understand, like here we say power is equal to torque into speed. Okay, so this is the power. And what is speed? Speed is 2 pi n upon 60. Okay, so this is our angular speed, and this is your linear, right? Angular speed, and this is in rpm. You can say not linear. Okay, now what happens that in terms of mechanical, if I write this power, I will write it like j j omega, oh, j alpha and omega. Okay, so this is j alpha is your torque. So torque, I can write j into alpha. So what is j? J is inertia. Okay, inner inertia. Inertia. And what is inertia? It is kg meters. Okay, so for the electrical side, the power was torque into omega. Okay, and then what we have right for the mechanical side, power was j alpha and omega, right? So I have told you that what is j? J was inertia, and that inertia was kg meter square. So look at the unit is weight upon area. Okay, weight of the machine upon area, right? And alpha is the angular acceleration. Alpha is the angular acceleration acceleration angular acceleration. Now alpha is angular acceleration. Theta, I'm defining one more quantity, that is theta. Theta is angular displacement, and omega as angular speed. Okay, now if I write it, how will I write? Omega is equal to d theta by dt. Okay, rate of change of angular displacement with respect to time will be angular speed. And what about alpha? Rate of change of omega with respect to time will be your angular acceleration. So I can write it like d double differentiation of d theta by dt, right? So here, if I write angular acceleration is in terms of d theta by uh, dt. Okay, and omega is your angular speed. Okay, now, so what happened that p is equal to j alpha into omega. What happened that we want a relation between, our string equation makes a relation with our moment of inertia or angular momentum. Okay, so angular momentum m, this is our m, and that is j omega. So this is what angular, this is our moment of inertia, and or it can be said as angular momentum. So if you have read in physics, momentum is mass into velocity, right? So mass into velocity here, J defines the mass and omega is the velocity. So J is analogous to I can tell it is analogous to mass of a body, right? So analogous to mass of the body. So now what I can write our equation with respect to m p. So p I can write m into alpha, and m into alpha I can write it like m into d square theta upon dt square. Okay, so that's what our swing equations. One side says that the power is moment of inertia multiplied by product of moment of inertia or angular momentum with respect to your acceleration. Okay, so what can be the unit of m? Unit of m can be defined as joule per second upon mechanical radian. Okay, now this quantity is mechanical radian. So in terms of if the pole is different, means that there is a relation between electrical poles, electrical degree or electrical radian, and mechanical radian, right? So our electrical radian will be equal to mechanical radian multiplied by number of poles by 2. Okay, so what I can write about your m m was joule per second, right? And divided by mechanical radian. So I can write that in electrical terms. If I express m, I can write joule per second upon mechanical radian into p by 2, right? So this is your joule per second divided by electrical radian. Okay, so finally, if I express actually this is a very heavy machine, so joule will can be converted into a higher power, that is megajoule. Okay, so I'll be using that energy, so I can write it megajoule second electrical degree, electrical radian, and you can convert that radian into degree also, right, by multiplying with 180 by pi. So if you multiply it, so you can, so that's the unit, megajoule second per degree. Okay, now as I have till now what I have expressed, that mega m is j into omega, and I have expressed p as m into alpha, and that m into alpha was m into d square theta by dt. Okay, now here this is the major relation you need to know about your power system stability. I know it is somewhat complicated, but you might have got clear idea what is happening with the mechanical system. I'm not expressing till now. I have not expressed in electrical side. I have just expressed all those things into a mechanical side, right? So here m is your j into omega. I have expressed that j was analogous to mass, and m is analogous to angular momentum. Okay, so this momentum is the major factor for your acceleration. Means once, if you are if you are suppose if your machine has more mechanical power than electrical power, so for a small period of time, that is called as transient period, there will be acceleration of power, right? Pa. So pa I can express as PS minus PE. So this acceleration power I can write as if now what happens if you have more mechanical power, your rotor will rotate faster, right? So that rotation or faster than the actual speed, okay, so that for a small period of time, okay, and for that small period of time, if that acceleration is more, that is uncontrollable, your machine can get into instability, okay. So that's why power I have expressed it terms of, like, I can write it Pm into alpha, that is mechanical minus mechanical power into, and this is our swing equation. Now here there is a difference. What difference is here? That difference is because of the theta. Now theta is the angular displacement. Now there are three different axes for your angular displacement. What are those? There is a reference axis, there is a stator field axis, and there is a rotor field axis. Now how do you define theta with respect to what? Because mechanical people, they don't know, or they are limited with this theta. They just term it like it's an angular displacement. But for our side, we have three different moving parts, okay. Now there is a rotor that is moving, there is an rotor field that is moving, and there is an electrical stator field also moving. Now if those three are moving, how will you select theta? Okay, now, and if you have a selected theta, how will you express that theta? So our swing equation is basically telling, if you can express that theta, you can you can get into swinging together. Swinging together means swinging together, that is coherent, coherent, and not swinging together, that is non-coherent, right? So this theta deals with the that thing, coherency and non-coherency. Non-coherency. Now if two machines are connected in parallel, if their theta varies in a same way, okay, in a same way, then I can say that it is swinging together. And if it varies in different ways, means different ways means what? Change in angular change. If two machines have same change, that means those two machines are swinging together. If there is a change in delta theta, and that change is different, that means that machine is having non-coherency. So what coherency actually means is that when you require more in electrical power, and you have under balance condition right now, just suppose that there is two machine system, one more machine is connected in here, and these two machines are working together. What happens if your electrical these two are feeding electrical power here? Now right now the two machines are operate in a stable state, means those two are those two does not have any disturbance. Now your electrical power has increased, so if your electrical demand has increased, you will definitely increase your uh, mechanical side. Once your mechanical side has increased, what happens? That it has to balance this. Now it can get more than electrical side because of your momentum shift, okay, because there is a mass of the system, whole system, there is a speed, and it is operating at a very high speed, and that acceleration will be, I know this acceleration will be for us very small seconds. Now just understand, you are riding a bike, and there is a car in front of you, okay. So if you want to dodge this car, if you want to come in front, what you do? You just accelerate yourself and then you come here, right? Now what you may, and you maintain that acceleration. That's what you do. Similarly here also, we will accelerate our mechanical side and then maintain that speed with this. So that's why uh, in the bike system, what you do? You accelerate, you once you get on past this car, you come in front and you maintain that speed. Okay, now if somebody will accelerate very high and that acceleration goes to more, creates more distance. Okay, so that's what somebody can have more acceleration, but what happens if that acceleration is unstable, that may create instability, so your bike either can get into accident. So that's what acceleration means. How you can increase the speed so that you should remain in the stable condition. That's what here machines also tells you that only. Okay, now this acceleration will change your angle of angular displacement. Okay, now if your angular displacement of these two machines changes together, that means the electrical effect on these two machines is same. Okay, that means these two machines are operating under same, getting that effect same. Okay, now if these two machines the, that I can say that it is having coherent. Now it is operating in coherency. Now what happens if you increase the electrical side, you increase the mechanical side, but what happens that one of the machines delta or acceleration increases, but the other does not change. So what happens? Other does not change, or other remains constant. Okay, so what happens, all the electrical effect comes to one machine. Okay, and one if all the effects comes to one machine, then there is a chance that it may go to instability. Okay, there is a chance it may go to instability. Okay, so here I have expressed in theta. Now this same theta changes to delta in our stability curve, power stability curve. Now I'll tell you in the next slide, I'll tell you how it changes to delta. Okay. Now here is the rotor. Here you can see this is our rotor axis, and this rotor axis has three different axes. Now this first one, this axis, I am referring it as reference axis. Reference axis. Okay. This axis is your stator rotating axis, and this is our stator field rotating axis, and this is our rotor field rotating axis. Now I've talked about theta in the previous lecture, previous part, because theta is the angular displacement, and that angular displacement is having a function of t. Okay, uh, this because if you differentiate with double differentiation of your theta, right? Now if this theta is a constant, the differentiation will result in 0 if it is constant, so there is a no acceleration part. Okay, so and it has to be in a differentiation part. Now here if you check here that there is a rotor axis, there is a stator here, and that stator, what I can see if I observe in from here, that I will see that rotor is rotating, and if rotor is rotating, that means there is a change in theta. I'll see if I assume that there is this is my reference axis, and this reference axis changes it with respect to the rotation, right? Now what happens is that we don't know about the change in the delta t and change in gamma t. So there is some relation. What I can say, that it's what imaginary assumptions is that I have assumed that your theta t is the angle between your reference axis and your rotor field rotating axis. Gamma t is the angle between reference axis and rotor field rotating axis, and your this delta t is the angle between delta t is the angle between rotor field and stator field. Okay, so this is the major part. Now what I can write, that theta t is sum of gamma t plus delta t. Okay, so this I can write. Now what is gamma t? Gamma t is the angular displacement between stator field stator rotating field and reference axis. Okay, so I have told you that omega, that's the speed, uh, it is the differentiation of your angular change in your angular displacement with respect to time, right? So what I can say, that theta angular displacement is, if you integrate, you can write it omega t, right? The same, just integrate it, you'll get this, right? Now similarly, gamma t, what I can write, gamma t is the angular displacement, but there is an angular displacement with what? So I can write omega r into t. And what is this omega r? Omega r is the angular velocity. Omega r is the angular velocity between stator field field and reference axis. Okay, reference axis. So this is our, so omega r was this. So what I can say, that gamma t is omega r into t. Okay, now gamma t is omega r. So what theta t will be? Theta t will be delta t plus gamma t, and gamma t was omega r into t. Okay, now if you differentiate d theta t by dt, what I can write, it will be d delta t upon dt, and here omega r. And again, if I again double differentiate, because we need acceleration, what I can write, dt square is equal to d square delta t by dt square, and here this omega r is now constant. Okay, after first differentiation it get omega, so it is 0. Now what I can say, that from here you can say that d square delta t, d square theta t upon dt square is nothing but the change in delta t with respect to, and that is what your alpha, that is your angular acceleration. So what our mechanical side is angular displacement, what we see is nothing but the change in, or you can say that the angular acceleration, whatever you see from the outside, is actually the change in the angle between your stator field and rotor field. So rotor field and stator field. So this is what the change is there. So I have expressed, I can say that d square theta t upon dt square is equal to d square delta t upon dt square, that is your alpha. So Now if I put this value in our swing equation, what I was our swing equation we left about m into alpha, that was ps minus pe. Now m into d square delta t upon dt square is equal to ps minus pe. More clarity, I can write d square delta t upon dt square is equal to ps minus ev upon excess sine delta. Now this sine here, this is our electrical power. Okay, now here this swing equation, I can say that this swing equation is a non-linear. Okay, this swing equation is a non-linear differential equation. differential equation Okay, non-linear differential equation, and it describes the position of rotor, with respect to stator field, with respect to stator field rotating field. Okay, stator rotating field as a function of time, of time. Okay, so this is the most important relation, and before I know that you have derived this relation, but you need to understand what is happening. So this describes the relation between your rotor with respect to the stator field. Okay, now there is one more term, that is h. We'll define this, okay, in the next lecture. What is h? And here from h only we will go for the coherency part. Okay, okay, thank you.